scientific research at the Weizmann Institute. I would like to particularly thank our speakers today, Professor Aharonson, President of the Weizmann Institute, and Professor Aharonson, Head of the Ellen Kimmel Center for Planetary Science. I will also personally thank for their help in organizing this event, Abhishek Kishel from the Department of Hospitality and Conference, the President of the Mexican Association, Silvia Gerson, and the Coordinator, Paula Gallego, President of the Argentinian Association, Dr. Hugo Sigman, and the Director, Florencia Arbizer, and Mario Fleck, from the President of the Brazilian Association, and the Director, Claudia Isler. We are very happy to see many of you joining us today. Professor Aharonson will share with us an update about what has been happening on campus since the outburst of the coronavirus pandemic and where we go from here. Professor Aharonson will be our main speaker and will discuss his exploration of our solar system. Before we begin, please make sure your microphones are muted. We will open the session for Q&As at the end of the talk. We will try to answer as many questions as possible. You are welcome to send questions via the Zoom chat. We are pleased that Ariel Segal, a Weizmann supporter and a member of the Argentinian Friends of the Institute, will introduce Professor Aharonson, and will also manage the Q&A. I now would like to hand the microphone over to President Aharonson. Please, Alon.
Thank you, Danny, very much. Shalom, everyone. It's great seeing you all our friends in Latin America. Thank you very much, Hugo, on this introduction, this discussion about the virus is was extremely interesting for us. So I hope everyone is coping well with the situation. I know these are extremely challenging days to all of us. And I hope that solutions will come soon. Hugo just updated, maybe mid next year, we're gonna have available vaccine, unless the virus will decide to disappear before, which is hard to believe. But we have quite a challenging winter in front of us. And I hope future will look brighter and be able to meet again in person. As I mentioned before, and many of you received those information, the Weizmann was extremely active in the last few months around the COVID-19. We have 65 groups, which is 25% of all the research group at the Weizmann, doing research project on and related to COVID-19. And it's not only scientists from the biomedical field, but also scientists coming from physics and computer science, mathematics, chemistry, and more. I think I spoke about this quite extensively in the last few months and in many meetings. It's also available in our website. And I really wanted to focus more on where we're going from here. So despite the fact, Corona definitely affected the science, not only the Weizmann, but worldwide, more focusing toward the research on infectious disease and COVID-19. At the same time, we did our best to continue, maintain, and push forward new initiatives and continue doing the science that we are doing in the different fields, all the way from cancer research to immunology to physics, astrophysics. And we have a fantastic speaker today, Professor Aharonson, which will give us a glimpse into the planetary science, which is also one of our major flagship for the next few years. So it's very important for me that you will know that despite the situation, despite the restriction we have here and around the world, and the fact we cannot travel, we continue thinking ahead, developing our vision to the future of this institute. And I will just mention very, very briefly three main flagship projects which we are currently pushing forward. Before that, I would like to mention really great news because this has been announced only last week, and this is the new Leiden ranking, which is a ranking that is published every year for many years and is looking on the top institution based on the impact of the publications. And they look on the top 10%, 5%, or 1% of publication in all fields of science. And Weizmann, again, has been ranked in the top 10. If you look on the top 10%, Weizmann is number 8. And if you look at the 10% and the 5%, we're number 9. If you start breaking this into fields and you look on the biomedical, life science and biomedical, Weizmann is rated number 4 worldwide. And this is not normalized to the size. And if you look on the top 10 list, started with the Rockefeller, Harvard University, MIT, all the top 10 are US, meaning the Weizmann is the only non-US institution in this list. I think while we have to be very careful with this ranking, it's nice to see that continuously every year the Weizmann is located in the top 10 of this list, and probably say something also about our philosophy and how we think and how we conduct science in this institute. So very, very briefly, not taking too much time from Oded, I would like to mention the 3 main flagship projects that we are currently pushing forward. And the first one is AI, or artificial intelligence. All of you know the importance of this important topic now almost in every field of science. And this is mainly due to the fact that we are generating so much data currently, regardless of the field. You know, my field, neuroscience, but also definitely planetary sciences, but physics, chemistry, genetics. Currently, scientists are generating much more data they can actually handle, or have the ability to extract important information out of this data in classical ways, or using regular statistics and other methods. So this big project have 3 parts. One is to provide our scientists with those strong computers, those HPCs, high performance computing, which be able to do these heavy calculations, recruit those amazing engineers and scientists from the field of mathematics, computer science, and physics, who can develop those tools. And of course, here we are competing with Google and Amazon, which surely can pay much more than we can, but we provide those engineers and scientists the ability to do exciting science and interact with our scientists. And the third part is supporting the research itself, not only people from mathematics and computer science, which generate or build or write those algorithms and machine learning tools, but also expert, or having those AI experts spread throughout the campus and become expert in AI in neuroscience, AI in planetary science, and AI in physics, and so on. This is not a building project, this is an umbrella project which is gonna go throughout the campus. The second project is about neuroscience and brain sciences. And as you know, one of the strongest hubs on campus is brain and neuroscience. We have currently almost 40 research groups on campus, but they are spread throughout the different departments and faculty. And as you know, this complex organ is definitely the last frontiers in biomedical sciences. This is the most complicated organ that we know the least about, and it is associated with the most devastating disorders, all the way from neurodegeneration, Alzheimer, Parkinson, dementia, ALS, all the mental disorders, depression, anxiety, post-trauma, eating disorders, schizophrenia, autism, and many more. And we neuroscientists realized years ago that in order to learn and to cope with understanding this complex system, we need to bring people from different expertise. It's not enough to bring people from the biomedical field. You need people from physics, from mathematics, from computer science, chemistry and put them together, even psychology, to put those people together that you will be able to interact. So this very big project is building a new home for the neuroscience on campus, bringing all these scientists to have a physical interaction and provide them with all the infrastructure and the state-of-the-art tools in order to be. And I know that Mario took on himself, together with Danny, to support one of those centers on neurodegeneration. We have this big project is composed of 10 different centers dealing with 10 different aspects. The last big flagship project is on astrophysics and particle physics. And Oded will tell you a little bit more today about what he is doing, and while not being part of physics, but on the chemistry faculty, of course, what he's doing is extremely relevant to what we like to name now the Weizmann space program. Okay, and it's currently on the Weizmann, we are building a satellite, which is a very, very unique satellite with many collaborators around the world. And this satellite, unlike other satellites, which actually look down to Earth, this satellite look up to the universe and is aiming to capture supernovas, those blasts of stars, which are considered the source of the materials in nature. NASA agreed to launch this. We have the support from the Israel Science Agency, from the European Space Agency, sorry, from the German institution, the Helmholtz, which provide us with the camera. This is $100 million initiative. We already have a deadline for launching, which is mid-2024. And this is extremely informative. And if it will be successful, it will position the Weizmann in a leading institution in the field of astrophysics. Of course, we can tell you much more about each of these, and there's many other important but smaller projects, but I think I should stop here and let Oded, the main speaker of today. So thank you very much for joining. I'm looking forward to seeing you all in person, hopefully soon. Ugo, now it's your responsibility. As soon as we have the vaccine, we're gonna come. So thank you very much for all of you, for the support, for the friendship. I know it's hard, but you know, in one way we cannot travel, but we have the opportunity to do this type of activities. So thank you, Danny and Avishag, for organizing. You have a fantastic series. It's only 3 scientists, but I'm sure at the end you will ask for more. Really 3 fantastic, amazing scientists from 3 different fields. So thank you very much, everyone, and enjoy.
Thank you, Alon. It's an honor for us that you have decided to open this series of meetings for Latin America. You are always with us at our events. Thank you very much. Now I would like to invite all of you for the premiere of a short video about our main speaker today.
Hi, today we will climb up to the top of the Kepler Particle Accelerator to meet Professor Oded Aharonson. Come join me.
Hey Andrea, welcome to the Kepler Observatory. I'm sure you all know about all the excitement that's been surrounding the moon and Mars. We've had our own Israeli mission to the moon, Bereshit, that nearly made it to the surface. I was the mission scientist for that. And for Mars, we have 3 spacecrafts launching just in the next month. There's an American mission, a Chinese mission, and 1 mission even from the United Arab Emirates. We're going to land on Mars, we're going to orbit Mars, we're going to study the atmosphere, we're going to study the surface. Things are exciting. My own lab has been focusing on exoplanets. These are planets that are orbiting other stars other than the sun. They're fascinating. They're potentially the most important intellectual advance, I think, that astronomy has made in the last couple of decades, because they teach us that our solar system is not unique, that there are many, many solar systems around many, many stars all throughout the galaxy. We're studying them using telescopes, using the Kepler Space Telescope, using data from the ground, and pretty soon we hope to study them using ultrasat, Ultrasat is a mission from the Weizmann Institute that's designed to look for enormous astrophysical explosions in the universe. But the way I want to use Ultrasat is to use the camera on board to look for these tiny exoplanets in ultraviolet light. So there's a lot going on, things are exciting. See you outside. Now I'd like to share with you why this is my favorite spot on campus. I can talk to you about the spectacular view around us with campus laid out here. I can tell you about the telescope inside, which we use both for educational purposes and to study the instruments that we're building for satellites. But I think the real reason that I like to stand out here is because standing up on this magnificent structure that the Weizmann Institute built, and next to this telescope that the Institute invested in, I really feel all the support that Weizmann has placed in us scientists, and I really feel a little bit closer to the stars.
Good evening. I am Ariel Sigal, hailing from Buenos Aires, Argentina. I am a member of the Argentine Friends of Weizmann, and I've met with many of you last year in Rehovot. It is my great pleasure to introduce to you an Israeli in the 21st century. Professor Oded Aharonson received his degrees in applied physics from Cornell University, served in the Israeli Air Force, earned a PhD from MIT, and was a professor at Caltech for 10 years, before moving to Weizmann, where he leads the Center for Planetary Science. Professor Aharonson, as he said, studies exoplanets outside the solar system. He creates unique mini environments in his lab to simulate as much as possible the conditions on Mars and other planets. He has been involved also in the science of several space missions, including NASA's Mars exploration rovers. And as he said, he was a mission scientist for the Space Bereshit lunar lander in April of last year that launched a satellite to the moon. Please remember to post your questions on the chat, and Oded, you have the floor.
Great. Thank you. Can everybody hear me pretty well before I switch to full screen view? Okay. So let me share my screen. How's this? Can everybody see the correct screen now?
Yes,
give me some nods.
Perfect.
Okay, great. Okay, well, it's a pleasure to be here. Thank you for giving me your attention. I realize this is a bit unusual. It's also unusual for me. I prefer to speak to people that I can see and touch, but at least I can have this opportunity to share with you some of the things that I've been working on, and also more broadly on campus, people are working on. So thanks for your attention. You know, I thought what would be fun for us to do is to kind of take a cruise, take a trip through space. We'll launch from Earth, and maybe I'll use the little bit of time that I have to take you through a short tour of the solar system. And after we're done with our short tour of the solar system, we'll even leave our solar system and talk a little bit about exoplanets. And then at the end, if I still have your attention and we still have a couple of minutes, then we can have some fun and maybe talk about life in the universe and kind of speculate about some things that many times scientists are shy to lay out. So here's our solar system. The 8 planets, or here there are actually 9. There was used to be another planet called Pluto that my guy down the hall from me at Caltech is responsible for demoting to no longer a planet. So now we have 8, and we're going to start here close to Earth in our own moon. Now, the moon has been a subject of interest for ever since mankind and men and women stared up at the sky, and there are legends around the moon. There's science, there's politics even that had connected to the moon. But I thought I would just highlight for you some of the reasons why the moon is making a renaissance. I think it's having a renaissance and kind of making a comeback in the space agencies throughout the world, both in Israel, in the United States, in Europe. There are even contributions from Latin America to missions that are going to the moon. And the first reason that I think is really important and is easy to connect for everybody to connect to is water, right? Everybody knows that life, at least as we know it, requires water. By the way, there are some life forms, spores, that can survive without water for a very long time. They basically go into hibernation and they don't need any water. They can survive almost a very wide range of temperature and pressure conditions, but they don't multiply in this way. For life to thrive, it needs water. And what we now know is that the lunar poles, the polar caps of the moon, have some water in them. The idea is that you see here the craters on the moon, and because the moon spins in a direction such that the sun is always above the equator, the spin axis of the moon is always perpendicular to the sun, any crater near the pole of the moon, you can imagine with your own imagination, doesn't get very much sunlight because the sun can't peek over the rims of the crater. Those craters stay permanently shadowed and extremely cold. The coldest place in the solar system is actually the poles of the moon, maybe as low as minus 230 Celsius or something like this. And any water molecules that might bounce into these permanently shadowed craters would never bounce out. Now, this has become a source of tremendous promise for future exploration because men and women hope to go back to the moon and land on the moon and maybe use the moon as a base for future exploration of the solar system. And water is an essential ingredient to accomplish that, both for consumption, but also because if you have electricity, you can separate the hydrogen and the oxygen from the water molecule and make rocket fuel on the moon. So basically, water is the most important essential ingredient. And now we know that there are some deposits of H2O on the moon. Of course, they're very cold, so we need energy to extract them. But energy is a solvable problem. Mankind knows how to make energy. The way this water was actually originally discovered on the moon, I thought I would mention it because there's a connection to, I think, a member of this organization. There's a gentleman, I haven't seen his name online, Martin Kushner, who's a nuclear physicist. Is he online? Anyway, it's the very same nuclear physics that, okay.
Yeah, from Mexico.
From Mexico, exactly. It's this basic nuclear physics that I'm sure Martin can attest to, that was used to find these water molecules on the moon. It's basically the interaction of neutrons as they impact the lunar surface and set off a cascade of gamma rays. That's the very same nuclear physics that was used to find this water on the moon. So Martin, wave if you can hear this or if you agree with what I'm saying. The next bit of story that I wanted to share with you about the moon is actually maybe the most fundamental question of all, which is how the moon was made. And this is something that my group has been involved in for, I don't know, at least 7 years, basically since I came to the Institute. We published several papers on this. A very talented student who's now a researcher in the United States that basically wrote a paper about how the moon, challenging the conventional story about how the moon was made. Now, as you'll see, the moon, the question of how the moon is made, because everybody thinks the moon was made by an impact onto the Earth, this question is not esoteric. It's basically intimately connected to how Earth itself was made. Basically, Earth and the moon share a common history, and by understanding better how the moon, the formation of the moon, we're basically understanding better how Earth itself was born. So I think this story about making the moon out of a collision is really important for us to understand. The conventional story has the moon made as a fragment from a collision of maybe a Mars-sized object that hit the Earth, ran into the Earth very early in solar system history, 4.5 billion years ago, and ripped a chunk out of the Earth from which the moon solidified. But several decades ago, astronauts went to the moon, picked up some rocks, brought them back to Earth, and then analyses in the lab showed that the composition of the moon, these pieces of moon rocks that the astronauts brought back, was remarkably similar to the Earth. Basically, these rocks look just like terrestrial material, except if you put it in a pressure cooker and cook it for a while. Okay, you bring it to high temperature, you get rid of all the volatiles, get rid of all the water that the Earth might have, boil off all the elements like the volatile elements like CO2 and water and other things that you get rid of at mid to low temperatures. And that's how you get the moon. Take the Earth, boil it, you get the moon. And this disagreed with the story of making the moon out of a single collision, because if you think about what I just said, you understand that if something like Mars hit the Earth, then pieces of that proto-Mars would also contribute to the new forming moon. So a very legitimate question is, why does the new moon look exactly like Earth and doesn't contain any contamination from this original body that hit the Earth? And as the measurements got more and more precise, this problem got worse and worse, because now we know that the moon is identical to the Earth in terms of its chemistry, in terms of its isotope composition, to something like parts per billion. Okay, so for every 999 million particles that that make up the moon, there's only one that may have not come from Earth. Okay, so this is a real problem, right? It doesn't make sense, this story. And the way we sought to fix the theory is to say, okay, the moon did form by a collision. There's a lot of evidence for this. Something hits the Earth, you make a disk, the disk makes a moon, and the moon starts spiraling outwards early in solar system history. But then what Maluka, my student, and I thought is, why invoke this impact happening only once? It's much more natural to imagine that the history of the solar system is governed not by these special catastrophic events, but rather by events that happen more than once, again and again. So it's much more natural to imagine that this impact might have happened again, that instead of having one huge Mars-sized object hit the Earth, maybe there were 2, 3, maybe a dozen impacts, each of which hitting the Earth in the first, say, 100 million years of history. And each one of them would make a disk and would make a moonlet. And these moonlets would basically, we did all the dynamical calculations to see what happens. And indeed, they chase each other out. They spiral away from the Earth and chase each other in their orbit around the Earth until they merge, until they catch each other, merge, and collide and make the moon. And this really helps with this isotope crisis, as it's come to be known, because if you make the moon from multiple pieces instead of from just one piece, then each individual piece could be quite different from the Earth. But at the end, the average of all the pieces together that make the moon is a lot more similar to the Earth than each individual pieces has to be. So the best analogy that I can give you is, let's look at the people that are attending this meeting, right? If I look at the height of each person in this meeting and compare it to the height of another person, I will get a very different answer, right? Some people are taller, some people are shorter. But if I divide you into two groups and I look at all the average height of one group and the average height of the other group, the two averages are going to be a lot more similar to each other than each individual person. And this is basically what helps explain how the average moon made up of multiple pieces looks like the average Earth. Does that make sense? Was that clear? I always ask my students on Zoom, I'm teaching via Zoom now, so if you can nod, this is, okay, great. So that's the story that we're telling for the moon. Before we leave the moon and go on to another object, I thought I would share this picture with you. This is one of my favorite Apollo images. You can see that the lunar base is off in the distance here. You can't quite see it, but there's an astronaut walking around this boulder and the vehicle. And the reason why I think this picture is, I mean, besides just its aesthetic beauty, right? The reason why this picture is almost emotional for me is, I think what this picture really helps, I'll tell it this way, you know, I met 3 astronauts in my life. I don't know if any of you ever met astronauts. I know 3 astronauts. I even have Buzz Aldrin's phone number. If you want, we can call him later. And I asked them, you know, for a scientist like myself, a planetary scientist, to talk to an astronaut is like to talk to, you know, a superhero, right? These people are like our superheroes, right? And to talk to 3 astronauts who have been to the moon, there's one question that everybody wants to know. And for me, it's, as I said, it's almost like an emotional question. It's not just a scientific one. And the question that I asked all 3 of them is, what is it like to walk on the moon, right? This is like every kid's dream. So what is it like? Can you tell me what it felt like to walk on the moon? And astronauts are very well-spoken people. They're selected partly because they know how to relate to the public. And they're also very individual people. So So, you know, they each have to be a little bit different. They don't want to sound generic. So they each make up their own answer, and the answers varied. But there was one element that I kind of collected from all the answers that I got that I wanted to share with you. And their experience, what they said about walking on the moon, was that it changes the moon from being this target in the sky, which, like in the picture that I showed you in the beginning, just looks like a disk. It doesn't even look like a sphere, right? It doesn't even look spherical. It looks more like a disk. It looks more two-dimensional. But when you actually get to the moon and land on it and walk on it, it changes it from being this thing that's painted on the sky to being a place that humanity can really imagine landing on and touching and maybe living on someday, and changing it from this concept to a real place for humanity is something that's really happening again now in the space explorations of multiple countries. And for me, this picture also kind of captures that. It kind of puts the moon in a human perspective. It makes you feel like, you know, you can imagine the moon as being a place where people can interact with. So with that spirit, I would say, you've probably heard of this Google Lunar X Prize. I'll tell you a couple of words about this incredible roller coaster that we went on in the last few years. This was an initiative to land on the moon by a private organization, so not by a government. We already know that governments know how to land on the moon, so Google wanted to stimulate lunar exploration by smaller bodies. And they announced this competition to get to the moon that several teams from all over the world entered, including one team from Israel that I was the part of, called Space IL, with the spacecraft called Bereshit. And Bereshit was a pretty special spacecraft because it was really designed with the express purpose to land on the moon. Originally, it didn't have a science goal. But, you know, when I met these guys, I said, you know, what are you going to do when you get to the moon? They said, we're going to land on the moon. I said, no, we have to do something scientific. We have to do something intellectual for this mission. And eventually, after arguing this over and over, we succeeded to include some science instruments from Weizmann and from other places on board. We had this component that NASA contributed that's a laser retroreflector that reflects the laser light. Here you see us installing this on the spacecraft. I'm not sure if you can see my cursor, but it's over here on the spacecraft. And the idea is that another spacecraft that I'm a member of their science team can shoot lasers at these collection of mirrors and measures the distance from Bereshit to LRO. Spacecraft launch happened out of Cape Canaveral, the historic launch pad where all the Apollo missions launched. All my students flew out to the launch. My baby daughter was just born a few days before launch, so I couldn't go, but they all had a science team meeting and a big party on Cocoa Beach. And one of them took this spectacular photo of Bereshit launching towards the moon. We took some pictures that you might have seen in the newspaper, including this one of home with the plaque that shows the contributions to the spacecraft. I think this is my favorite picture from Bereshit. This is actually my Zoom background for when I have regular meetings. Here you can see the moon. The spacecraft is coming out of the back side of the moon here. So this is the part of the moon that you can't see from Earth. And here is home, right? This dot right here is home. So I love this because it kind of gives you a perspective on ourselves from the moon. One of the things we did for the spacecraft at Weizmann is choose the landing site. We had to choose whether we land on the near side or the far side. So the first thing to say is, okay, we want to communicate with the spacecraft, so we better land on the near side of the moon from which you can see Earth. There are specific latitude ranges that the spacecraft can operate because of thermal constraints. Some of them have a magnetic field, which was the main goal of the science package of the spacecraft. So you can see the southern hemisphere has more magnetic anomalies than the northern hemisphere. But in typical Israeli style, we chose to go to the harder place, which is the northern hemisphere that has fewer magnetic anomalies. The landing site was in one of the seas in the northern hemisphere, these lava seas that are particularly smooth and flat, and that was the reason why we chose to land there. This is one of the last images that the spacecraft took before impacting at high speed the surface of the moon. So for those of you who don't know or don't remember, this was not a soft landing, but we did collect some data before we hit the moon. When we did hit the moon, we left our mark. This is some of my friends with the spacecraft I mentioned earlier, the NASA spacecraft that have a camera on board, took a picture of the place where we hit the moon, and you can see the before and after picture. So you can see before the spacecraft got there, and afterwards there's this big splotch in 2019. So we left our mark on the moon. And as I mentioned, we even collected some data during our last orbit around the moon. So here's the magnetometer data that I just recently submitted for publication. So that paper should be coming out soon. So this was a real roller coaster. It didn't end as maybe we all hoped. And another kind of shout out I wanted to put in, I'm not sure, is Shimon Picker online? I understand we have another gentleman.
Yes,
Sorry?
I don't see Shimon in this group.
I thought I would put this here because, you know, how Bereshit ended is a very interesting story on its own. This is the control room in the last minutes before landing. You can see here the control room at the Israel Aeronautics Industry, where the Space IL team is manning all the monitors. The control room is actually divided in two. This is half of it, and the other half is behind this window over here on the right, where I'm sitting together with the science team. This is called the experts room. And the reason why I thought I would put this in is because the design of the control room, which is what Mr. Picker, I guess, is an expert in, actually influenced the outcome. What happened in the very last minutes of Bereshit is one of the two IMUs, the inertial navigation units, stopped reporting positions, essentially reported a fault. This has never happened before on the way to the moon. Everything you can imagine happened on the way to the moon. The star trackers got confused. The spacecraft computer reset. Everything you could imagine that could have gone wrong went wrong, and still the spacecraft survived. We all actually already believed that the spacecraft was invincible because it had so many anomalies, but it still continued to operate perfectly on the way to the moon. But then when one of these two IMUs faulted out, the second one, there's two of them on board for redundancy because it's an important piece of equipment. There's two of them. The second one continued working and everything was fine. The spacecraft, as you can see in the simulation here, continued to make its way to the surface and everything was fine. But then the system engineer who's sitting over here behind all these people gave the command to send a reset command to the spacecraft, basically to reset the second IMU in order to bring it back to life, in order that we have the redundancy that we were planning on to bring that back. Now, here in the experts room where I was sitting, there was another gentleman that knew the spacecraft, and he was whispering, no, no, don't do it, don't do it. But it was already too late. The command was sent to the spacecraft. And because there wasn't a direct communication between, in my opinion, because there wasn't direct communication, the command was sent before we had a chance to consult. And it turns out that that command actually resets both IMUs, not just one. And when both IMUs got reset, the spacecraft computer had no measurements at all. And then it itself reset. And then the engines were turned off. And then the spacecraft hit the surface, okay? Now, I'm not looking for whose fault it is. I'm not trying to tell a story about what was wrong here. What I am trying to say is that if the right command had been sent or if no command had been sent, I don't know what would have happened. We didn't do that experiment, right? We did this experiment. But I think it is important to remember, and I'm sure this is part of the lessons learned from Bereshit, that this communication within the control rooms is actually a critical aspect of how to run the projects smartly. So I thought this was a nice connection to make. Let's zoom out again and get back to our solar system. And now from the moon, go to the next object of interest. This is actually my baby. This is where I started my career, and that's Mars. And everybody is talking about Mars these days because Mars is an object that humanity can really see itself settling on. And there's people like Elon Musk who set their targets on Mars. I was involved in spacecraft projects that explore the history of Mars, where the big question is whether Mars ever looked like the Earth. Mars doesn't look like the Earth now. It looks like the most frozen, most arid, driest places on Earth. I went to Patagonia a few years ago. It looks a little bit like Patagonia. I also went to Antarctica. It looks a little bit like Antarctica because the places on Mars, even though there is a little bit of water, the water is frozen solid on the ground. And the big question on Mars is whether we can find places that over Mars's history, either in recent history or in the deep history of Mars, were warmer and wetter than they are today. I'll get back to that point at the end, but I just kind of wanted to set the stage because the next thing I wanted to say is this is what our solar system looks like, right? So we have our sun, we have the planets orbiting the sun. But as you heard in the video, I really think that maybe in planetary science and in astronomy, one of the most important intellectual advances that humanity has made is to recognize that our solar system is not special, but as we stare up at the night sky and we see all these stars around it, and this is something that we only understand in the last 20 or 30 years, okay? This is a very, very young field. So if you ask people 20 or 30 years ago, are there planets around other stars? They would legitimately not know the answer. And what we now understand is that when we look at all these stars in the universe, they each have their own solar system, okay? Maybe not all of them, but many of them, at least half of them, have their own solar system. And there's this great richness and diversity of solar systems. Some of them look like our own, and some of them look very different from our own. So I think for me, looking at all these solar systems helps us have our own perspective at our own solar system. So, this is kind of goes back to some of the most basic principles of science of, whether the planets orbit the sun or the sun orbit the planet, how special is Earth, how special is life that formed on Earth, is life prevalent throughout the universe, or are we special and unique in some way? These are questions that are partly scientific, but partly also philosophical in nature. And for the first time, we have telescopes at our disposal now that help us answer these questions scientifically, not with religion, which has its place, not with guesswork, but with real scientific hard facts. And the way that this is done, and what we're doing in my group as well, is to look at how these planets cross their stars. So what you see here in this animation is a couple of planets that are crossing the disk of their stars. Now the planets are too small to see from Earth, but what I can see by measuring the light from the stars is the size of the shadow that the planet casts as it's passing in front of the star. And the idea here is to measure these shadows using very sensitive telescopes, and from that deduce that there are planets there and how big they are. And this is what we're doing with the NASA's Kepler Space Telescope, with tests, with some ground observatories. And as Alon already mentioned, with this mission Ultrasat that is now under very rapid development in Israel with multiple partners from around the world. And as Alon said, the idea of this satellite is to take basically technology that we know how to make in Israel that's been used for a while now, both for spy technology, but also for monitoring the terrestrial ecosystem, and to turn it upside down. Instead of to look down at Earth, to look up at the stars. I really like this because it's kind of like using this technology to look up instead of to look down. You look up at the universe, and you can start to find out things about the universe. I'm running short on time, so I think what I'll do is I'll skip what I had to say about Mars and just go straight to this, because I think this is probably something that would be fun for you as an audience. And that is, I talked a lot about what it is that we're doing in space. We're flying spacecrafts around the moon. We're flying spacecrafts to look for exoplanets around other stars with magnetometers and all these things. And I even told you how we're doing it, the kind of suite of instruments that are being developed, some of them in Israel, some of them abroad, to make all these measurements. But what we haven't talked about, and what a lot of times I think isn't being discussed in areas of fundamental science, in basic science. So we had this nice conversation in the beginning about finding a vaccine for COVID-19. Here, the why is very obvious, right? But at the Weizmann Institute, we're interested also in questioning very basic scientific questions, not necessarily questions that will immediately, that you don't see the immediate effect on human health, or that won't necessarily make us richer or more powerful. So why should we study the moon? Why should we study exoplanets? And I think it's a valid question, and one that basic scientists are often shy about answering, because for me, the answer is, it's not easy always to put into words, but for me, I wake up in the morning and this basic curiosity, this desire to know and understand better the universe around me, that's what drives me. But if I have to articulate this, if I have to translate this into words, then what I want to tell you is, what is the most important question that we should all that I want to answer? And I want to phrase it like this, okay? I'm going to answer this question with an equation, but don't be afraid. It's not an equation that you're supposed to solve. It's a very, very famous equation that a gentleman named Drake scribbled on an envelope. I actually saw the original envelope. It's posted at an radar observatory in the United States on the wall. And it's called the Drake equation, okay? Now, again, don't be intimidated. I think this equation, you're not supposed to solve it. Even though some people try to solve it, I don't think it's the right thing to do. I think this equation helps organize what we know and what we don't know about the universe, okay? And what this equation says is n is the number of aliens that we expect to make contact with us, okay? It's a little bit funny, but this is really what this is supposed to say. It's how many life forms are there in the universe that we should expect to be able to communicate with. And the idea of this equation is that this number, n, is made up of the product of all the factors that go into it. So R is the rate at which stars form, Fp is the rate at which planets form around stars. Of those stars that have planets, how many of them are Earth-like? That's Ne. Of those Earth-like planets, how many have life? That's Fl. So let's say life doesn't occur on any planet, so you need to multiply it by the percentage of planets that have life on them. But it's not enough to have life. The life better be intelligent if we're going to communicate with them. So you have to multiply it by the percentage of life forms that are intelligent. And of those that are intelligent, we have to multiply by the factor of those that can communicate with us, because some of them might not have developed technologies that send information over intergalactic or interstellar space. And finally, you have to multiply by how long these civilizations survive, because if they develop these technologies that are required to communicate, they might also develop technologies that are sufficient to destroy themselves, right? So you have to take all this product into account and to try to evaluate to what extent it's likely that we will, at the end of all this, find a civilization that's able to communicate with us. And I think this is really the most fundamental question. I'll say more about that in a second. But if we break this down for a second, from the story I told you, you understand that the rate at which stars form and the rate at which planets form, that's something that we're now studying with telescopes, right? So I told you some stories about this, about how we're finding exoplanets and we're finding solar systems around other stars. So this is something that astronomy and astrophysics is very busy doing, is to figure out what R is and to figure out what Fp is. And then there's some terms in this equation that I think are no less interesting. They're not my field, but they're no less interesting, like the rate at which intelligence arises. You know, we can argue about the rate at which that happens on Earth, but you know, the rate at which societies develop communication capabilities and whether they choose to invest more in schools or in weapons. All of these sociological questions, I think, contribute to these factors that influence N. But I think for me personally, the most interesting terms in this equations are the Earth-like planets and the ones that have life on them, these two terms. And the reason why these are so interesting is because right now we only know of one place that has life, and that's Earth, right? And with one example, the number of planets that are Earth-like, that could have life, could be anywhere from 0.0001 to 99.99%. We just don't know, because we only have one example that is hospitable to life, where there's liquid water and everything is comfortable, and indeed life arose there. But we don't know if this is like a cosmic accident, or whether every time there's a planet that's Earth-like, that has water and that has enough sunlight.
Oded, sorry, we have a few more minutes, so we need to summarize,
okay,
and we want to allow for 2 or 3 questions.
Yes.
If possible, okay?
Absolutely. This is my last sentence. So thank you for bringing that up. So what I wanted to say is, because we only have this one example, we really need to look for other examples in the solar system and beyond our solar system, for other environments that could be hosting to life, and figure out if life indeed arose there. Because then we will be able to tell the difference between whether life here on Earth is a unusual cosmic accident, or whether the universe is teeming with life. Thank you.
Thank you, Professor. Now we have some brief minutes for the Q&A until Danny tells us it's enough. Please remember to post them on the chat. I'll start with one of my own and then ask Mario's question. Professor, from your resume, it's obvious that you could have picked any research center, at least on this planet. Why Weizmann?
Okay, yeah, thanks for this question. I think actually I sort of answered that question inadvertently in the video that you saw in the beginning. For me, you know, I spent most of my adult life and my career in the United States in the best institutions at MIT and then at Caltech, which are really leading the world in planetary exploration. But at some point, I think it was a combination of 2 factors. One is I wanted to come back to Israel and make a difference. I wanted to come back to, I had this conversation when I was deciding whether to go back to Israel or not, with a scientist actually from the Soviet Union, from Russia. And we were sitting in Moscow, we were reviewing an instrument going for Mars, and he asked me about what I was going to decide. And I told him I wasn't sure because, you know, because I had this debate between Caltech and Weizmann. And what he told me is, for him, it was obvious what I should do, because he said, if you leave Caltech, somebody else another professor will come and will do great things. And, you know, they won't do the same things you're doing, but they'll do great things. But if you don't go to Weizmann, all of these activities and the space exploration, you know, 10 years ago, we didn't really have the right to expect all of this would have happened. But he said, all of these things will not happen if you don't go to Israel. And I think I chose to come to Weizmann because back then I really believed, and as I hope you can tell from this talk, it actually materialized. I really believe that Weizmann can give me the support to make a difference in Israel and to create a program in planetary science and to have students matriculate through this program. And I actually think this turned out better than I had any right to expect.
Thank you. Now we have a question from Mario Fleck. How many years ahead of us before having a permanent lab with people on the moon?
On the moon?
Yes.
Wow. That's a tough one. How many years? I think it's actually easy to envision. This wasn't the question, but you know, as a good scientist does, I'll change the question to the one that I do know how to answer. I think it's easy to imagine that people will go back to the moon in the next decade. Within maybe 6 to 8 years, I think we can land people on the moon again. I think it's really a question of motivation now, not of technology. It's much easier to go to the moon now than it was in 1969 when John F. Kennedy called us to go to the moon. And I think I would even say that it's easier to send people to Mars now than it is to send people to the moon in the 60s. Technologically, you know, we're so far advanced as a fraction of our global domestic or even individual countries' GDP, we have to invest less money, fractionally speaking, not in absolute dollars, but fractionally speaking, in doing this. So I think once we decide as humanity that this is what we should do, we can do it within, a decade. A permanent base is a little bit further along, because a permanent base requires infrastructure, it requires a good reason to have this permanent base. So I'm not even sure if I would rather have a permanent base on the moon first or go to Mars first. If we decide that that's what we should do, then I would say, not at the end of this decade, but by next decade, we could do it.
Okay, we have time for 2 more questions. One from Julieta Martino. How many exoplanets have been discovered so far? And do they resemble physically or chemically anything in our solar system?
Okay, great. This is one I know the answer to. Fantastic, great question. So roughly 4,000, take or give a few, exoplanets have been found. But before I told you that maybe half the stars in our galaxy have planets. So how does that work? You know how many stars there are in the galaxy? There's like 200 billion stars. So how come only 4,000 have been found? The answer is because it's hard to see them. So when we look at enough stars, we can do the statistics and figure out what is the probability that a certain kind of stars will have planets. And now we know that the answer is about half. And that means that we can easily see, with the techniques that I mentioned, roughly 4,000, several thousands of them. There's more and more being found all the time, and there's more and more information being found about them. My own group, I have a postdoc in my group named Aviva Fir, actually a staff scientist now named Aviva Fir, and he contributed to the paper that they found the planet around Proxima b, the closest exoplanet to Earth. This is a planet that actually is, you can imagine one day sending a spacecraft to it. It's 4 light years away. Part of your question was, what is the chemical composition of these places? It's hard to measure their chemistry, but we do know that some of them are Earth-like in the sense that they have the same size and the same mass as Earth. And if you divide those 2 numbers together, you get the density, and you get that the density is similar to Earth. So we found some planets that have the same density to Earth. So I think it stands to reason, it's logical to say that they have a similar composition to the Earth. So there's a great diversity. There's planets that are maybe very water-rich, and there's planets that are very iron-rich, and there's planets that are very rock-rich. But there are also places that look like the Earth.
Thank you. And last question. You mentioned Ultrasat, the Weizmann satellite that's going to look into deep space. What do you expect to find? And what do you think would be the impact on humankind?
Yeah, thanks for this question as well. So as Alon mentioned, the main mission of Ultrasat actually has nothing to do with exoplanets. It has to do with understanding the largest explosions in the solar system, these supernova explosions where elements are being generated that we're all made of. And this is the main mission. It also, some of you may have heard that last year there was a Nobel Prize for gravitational waves in physics. So one of the things that Ultrasat hopes to do is to find the flashes of light that correspond to the sources of the gravitational waves that are being emitted at the same time. So this would be a major accomplishment if we could look up in the sky and say, here is an explosion that made a gravitational wave, and here is the burst of light that came from it, because that burst of light contains a lot of information that tells us what happened during this explosion. So this will be a real game changer in the field of astrophysics to be able to detect that. And this would make a big difference, I think. And that's why it's the main goal of Ultrasat. As I mentioned, I'm trying to use Ultrasat kind of in a different way, because it's looking up in the, so this is now I'm switching to my personal goal, because Ultrasat is looking up in the sky all the time. Sometimes it will also catch some planets. And this is what I want to use it for.
Thank you, Ariel. It's time to conclude the sessions. I would like to thank again Professor Alon Hen and Professor Oded Aharonson for a fascinating talk. And to everyone, I invite you to join next week. We look forward to see you again on September 8th, same time, same place, different speaker. We are going to hear from Professor Sarel Flashman, who will share with us his part in the efforts to fight the COVID-19 virus. Have a good day and stay safe. Thank you. Thank you very much.